Hello, Luke. Welcome to Lesson 72. So today we'll be talking about factors that are sums and pyramids and cones. So to begin with, we'll start by talking about factors. And we've been talking a lot about factors. We've learned how to take a trinomial and factor it into a binomial. We've learned how to take usually a trinomial, but really any expression, and find common factors and pull out the common factors, basically the opposite of the distributive property. And today we're going to take it one step further, and we're going to talk about factoring of sums instead of just individual terms. So let's just real quick review. If I have something that looks like this, maybe, I don't know, ax squared plus 2ax plus 3. Actually, we'll switch that. Let's make it plus 3ax plus 2. If I have something that looks like this, 2a actually, we've learned recently how to recognize the common factors in these three terms and pull that common factor out. So in this trinomial, we would recognize that, hey, each one of these terms has an a in it, right? And because of that, we can pull that a out. We can divide the a out and then leave what's left over. So we have x squared plus 3x plus 2, right? Oops, 2. All right, and then once we have it at this point, we can recognize that, hey, we have a trinomial here, and it's in a form that we're familiar with. The x squared doesn't have any coefficient other than 1, and it's in the form x squared, then an x, and then no x. We can then try to factor this into binomials, and in this case, we certainly could. We would end up with x plus 2, x plus 1, and there you go. That's how we've been factoring. This is a continuation of that. It's just instead of recognizing this a, as we did here, which is just a single variable, we're going to recognize a sum that's common to all the terms. So if we look at this expression right here, we might be able to recognize that there is a common sum in all of the terms. And that sum is this x plus 1. All right? I've got an x plus 1 in every term. Okay? And that x plus 1 is a factor. That's, I guess, important to recognize, which means that it's being multiplied by the rest of the term. So this x plus 1 is being multiplied by the a squared, and this is being multiplied by the a, and it's being multiplied by the 6, right? So the x plus 1 is definitely a factor in each of these terms. And when it's a factor in each of the terms, we can pull it out, or we can divide it out, just like we did the a in this previous problem. It's just now we're kind of factoring out a whole bucket of a parenthesis bucket, you might say, where we're just factoring out that whole thing. So what we're going to do is we're going to take that x plus 1 and set it outside of a set of parentheses, just like we did with this a over here. We set the a outside the set of parentheses, and then we divided each term by an a. Okay? Same thing applies here, but do note that I kept the parentheses around the x plus 1. That's important, because we're pulling out this whole x plus 1, and it has to stay together as one kind of term, okay? So I pull out the x plus 1, and then I divide each of these terms by the x plus 1. And if you think of that, if I think of this term right here being divided by an x plus 1, we could recognize that the x plus 1 is going to cross out the denominator x plus 1. They're going to reduce, right? X plus 1 divided by x plus 1 is just going to be 1. They're just going to reduce out. So in a sense, it disappears, and we're left with just the a squared. Okay? Same thing applies here. If I divide this by the x plus 1, they cross out, and I end up with the negative, don't forget the negative sign here, the negative a. And then I have same thing here. The x plus 1 is going to cross out, and we're going to have the negative 6. Okay? So the beautiful thing here is we were able to pull that x plus 1 out, and it really kind of simplified that trinomial. Okay, it's kind of down to something that's a little bit more manageable and should look very familiar. Looking at this form, we would recognize that, hey, we could potentially break this down into a product of binomials, right? So we have our x plus 1. We're going to leave that, make sure we don't lose him. He's still sitting out here, x plus 1. But then we're going to take this trinomial here and try to set it up as a product. And so when we do that, this should be just, gosh, this should be, you should be able to do this in your sleep at this point. But we have an A. The factors, well, the sign here, negative, means we're going to have opposite signs here. And then the factors for a 6 in which they could combine to be a 1 would be a 3 and a 2, right? Because 3 minus 2 can give us a 1. So the 3, which is the larger number, is going to go with this sign, which is the negative, so it has to go with the negative, and the 2 goes with the other one. So there we have it. And if I wanted to do a quick FOIL check, I could. A times A is A squared. Negative 3 times A is a negative 3A. A and a positive 2 is a positive 2A. Combine those two, positive 2A, negative 3A is a negative 1A, gives me this. And then the last terms, negative 3 times a positive 2 is a negative 6. So that all works out. All right? So there you have it. We've taken this rather lengthy expression here, and we've reduced it down, or factored it down, into 3 factors that are sums. We have the first sum, x plus 1, second sum, a minus 3, third sum, a plus 2. But those are all factors for this expression. All right? So that is our factorization. All right, excellent. So hopefully that made sense to you. Bottom line, it's no different than what we were doing earlier when we were just looking at the single variable. The only difference is that now it's a sum and not just a variable by itself. Okay, very good. Let's try another one of these. And why don't you pause the video, try this one by yourself, and then we'll do it together. All right, so let's see how you did. So again, we're looking for things that are common in these terms. And hopefully you would recognize the common thing here is a sum. It's this sum, this x plus y. It's in all of the terms, and it is a factor in all of those terms. So we can pull that out. We'll just set it outside of our set of parentheses here. And then we divide it out amongst all the terms. So if we divide it out here, it's going to be lost, and we're left with x squared. Plus, here it'll be lost, and we have 9x. Plus, here it's lost again, and we have 20. And there we go. And then at this point, we see a trinomial in the correct form. And so we're going to try to separate that into its factors. So we have our 2 sets of parentheses. We have an x. We have an x. This positive tells us the signs are both going to be this sign, which is positive. The factors for a 20, we have to think about that for a second, but I think of 5 times 4 is 20, and I know that 5 plus 4 is 9, so 5 and 4 are going to be the right ones. Since the signs are the same, we don't care where we put them. We just want the 5 and the 4. And there we go. And maybe just a quick double check. Do the FOIL. X squared plus 5x plus 4x is a 9x. Last terms, positive 4 times positive 5 times a positive 4, positive 20. Good, we did it right. And there we go. That is factored. It's as simple as that. All right, excellent. Let's try one more here. So go ahead and pause the video. Try this one on your own, and then we'll do it together. All right, so let's see how you did. Again, we're looking for commonalities between these 3 terms. And we should recognize that, okay, here we have our sum, x minus 1. That's common to all 3 terms. However, is there anything else that's common to these terms? All right, let's look a little closer. Is there anything else? I also see an m that's a factor in the first term, an m that's a factor in the second term, and an m that's a factor in the third term. So we could also factor out an m. All right, so we're going to factor the m, and then we're also going to factor out the x minus 1. Again, note how I keep it in the parentheses. All right, what's that going to leave us with? Well, the m, we're just going to lose the m when we divide that out, and the x minus 1, we're going to lose the x minus 1. That leaves us with x squared plus 7. And then again, we're going to lose the m. We're going to lose the x minus 1. So we're left with 7x plus losing the m, losing the x minus 1, 10. And there we have it. And then again, we have a nice form here that we could hopefully break up into binomials. So let's try that. We know that we still have this m and this x minus 1. They don't go anywhere. And then we're going to have this double set of parentheses here. We have our x's. Plus sign indicates they're going to be the same, and it's going to be this sign, so they're pluses. And then the factors for a 10. Well, let's think about that. Factors for a 10. A 5 times 2 is 10, and a 5 plus 2 is 7. So 5 and 2 are the factors we're looking for, and it doesn't matter where we put them. And there we go. Again, if you want to do a quick check, you certainly could, but you would see that when you multiply these two out, when you FOIL them, you do get back to the original trinomial, and so you did it right. And there we go. That is our factorization. Excellent. All right. Now, let's move on from here and look at the second part of our lesson today, which is pyramids and cones. All right. They go into a lot of depth in this section in the book. We're going to try to kind of simplify things a little bit. Primarily, what they're trying to get across to you is how to find the volume and the surface area for pyramids and cones. All right, so let's get some definitions out of the way. So make sure you have your class notebook out and a pen or a pencil and write down these definitions so that you can study them. So the first definition is pyramids. What is a pyramid? Well, think of the pyramids of Egypt. What do they look like? They have a base, and then they have kind of these triangular sides that come to a point at the top. All right, so that's basically what this is saying. A pyramid is a geometric solid with one face. Remember, each side is called a face. Okay, so one face, which is a polygon, and we call this the base. So a polygon would be like a square or an octagon or a pentagon. You know, it's made up of straight lines is the bottom line. It's a polygon. It's a closed shape made up of straight lines. There aren't any curves in the base for a pyramid. All right. And the other faces are triangles. Okay, so there you have it. The other faces are triangles. The bottom face or base is a polygon of some kind. All right, so if you look at these four shapes here, we have several different examples of pyramids. The first one's a very straightforward one. The bottom is just a rectangle. Okay, so that's the base. And then you can see again, picture all the other faces. They're all triangles. Okay, the next one, we have a hexagon as the base. So now we have more faces, but the faces are all triangles again. It's just the base has changed. And then we have the heptagon, same thing. It's just now, what is that, 7 sides to the base. Okay, and then the decagon as well. So we've got all kinds of different ways that you could write or draw a pyramid. Okay, one other note that I might make on this is that some pyramids are going to be right pyramids and others will be skewed. So, for example, in this first pyramid, if you kind of think of it, the point is at the center of the rectangle down below. Okay, it's going straight up, which would mean that all the triangles are the same size. Now, this one, I don't know about this one. This one's a little bit tricky. It almost looks like maybe this top point here has been kind of pulled this way a little bit. It doesn't quite look straight up and down. Okay, and if it's not straight up and down, then it's slightly skewed, which would mean that these triangles are all a little bit different in size. Okay, in the book, when they give you pyramids, they are focusing primarily on right pyramids. Right pyramids. And that just means that they are pyramids where the sides are all going, they're all equal. So the vertex or the top of the pyramid is straight up from the center of the polygon base. Okay, it's straight up and down. This pyramid is not leaning in one direction or another. All right. Okay. Excellent. Let's move on here. Another definition: cone. All right. A cone is like a pyramid, except its base is a closed curve instead of a polygon. the only difference, all right? But it's kind of an important one. So if you look at the base of a cone, unlike a pyramid, it's circular in nature, all right? There's curves to the base of the cone. There are not curves to the base of a pyramid, all right? And that totally changes the makeup of the faces, okay? Because with a pyramid, you've got this polygon base, which gives us a bunch of faces, and they're all triangles, right? If you're talking a cone, you have a circular base, which means you don't really have a bunch of triangular faces. It's actually a curved surface as you go up. You might say there's only one face. It's a curved face as it goes up. All right? So that's the key difference between a pyramid and a cone. All right? Now, again, just like the pyramid and the pyramid, we can have kind of a right pyramid, which just means it's going straight up, right? The apex, or kind of the peak of the cone, is directly above the center of the base. Okay? It's going straight up, not leaning. And then you have the oblique cone, which just means that it's offset, that apex is not on the center of the base. It's skewed off to the side. All right. So again, it just means that the cone is kind of leaning one direction or another. Okay. And again, for our purposes in the book, most of the time they're going to give you just right cones. Okay. Now there are a couple of things that we can talk about as far as definitions go with right cones. You have the vertex, which it's nice to know, but that's not key in this case. You have the height, which is important. We do need to know the height, and the height is just simply what it sounds like. It's the length of the distance from the base to the vertex, to the very top. Okay, that is your height. Now, there's also a slant height, and that's also going to be very important. We're going to be talking about that. We're going to be using that in some of our formulas. So the slant height is the length of the side of the cone, you might say. Okay? So again, this length from here, kind of following along the side up to here, that length is not the same length as the height of the cone. The height of the cone kind of starts here and it goes straight down, right? This is the height of the cone. That length is going to be shorter, actually, than this slanted side length, all right? So this slanted side is given the definition slant height, okay? That's how we measure it. It's called the slant height, all right? And then the height is just the overall height of the cone. Two very different things, though, so keep that in mind, all right? Very good. All right, let's move on. Now we're going to get to kind of the meat of the arguments here. We're going to talk about the formulas. All right, so what is the volume of a pyramid or cone? Well, the good news is that you only have to memorize one formula for the pyramid and the cone volume. Okay, it's the same. So it doesn't matter if it's a cone or if it's a pyramid. The volume formula is actually going to be the same thing. All right, and this is it. It's 1/3 times the area of the base, okay, times the height. All right, that is the formula for the volume. And maybe I should say that, the V, volume. 1/3 times the area of the base times the height. And that's the formula for the volume of a cone or a pyramid, either one. Okay, the only difference here is your approach to finding the area of the base is going to be different, because the area of the base in a cone is circular and the area of the base in a pyramid is a polygon. All right, so if I have this shape right here, this cone, and they're telling us that the radius of the base is 5 meters, okay, and let's just say that this S, which is the slant height, let's give that a number, just for the sake of filling this out. Let's say the slant height is, oh, I don't know, 7, and let's say the height is 6. So we'll make the height is equal to 6. All right, so how would I find the volume of this cone? Well, it's pretty straightforward, right? Once we know the formula. So the volume is going to equal 1/3 times the area of the base. So we need to figure out what the area of the base is. All right, now the area of the base, because this is a circle for a base, we have to think about the area of a circle, which is pi r squared, right? So pi r squared means in this case pi times radius, which they tell us is 5. 5 squared is 25. So the area of the base is 25 pi. All right, so I'm going to say that over here, 1/3 times 25 pi. All right, and then lastly, we need to know what the height is, because we need to multiply it by the height. Now, remember what that means. Height is this number. It's not the slant height. It's the actual height, the overall height, which in this case is 6. So we're going to multiply this by 6. Okay? And if we do a little multiplication here, I could say that 1/3 times 6, because this is all multiplying, it doesn't matter what order I do it in. 1/3 times 6 is nice and easy. That's going to be 2. So that'll be 2 times, 2 times 25 pi. All right, and I can multiply that out and get 50 pi. And then you could do this on your own. 50 times pi is 50 times 3.14 roughly. So, we're looking at, 150, something over 150 meters squared. Or excuse me, meters cubed volume. Okay, excellent. So that is how you define the volume of the cone. Pretty straightforward once you know the base. Or excuse me, once you know the formula, and then from there, figuring out the base. All right, now let's take a look at this pyramid here. All right, now here we're trying to find the volume again. So the formula is the same. It's volume equals 1/3 times the area of the base times the height. Okay, so what do we have for a base here? That's key. Here's the base, right? It's this polygon at the bottom. So it looks like it's a rectangle. And how do we find the area of a rectangle? The area of a rectangle is length times width, right? So 10 times 8 is going to be 80 inches squared, okay? So the volume is going to be 1/3 times the area of the base, which we found to be 80, times the height, which they give us right here, which is going to be 6. And there we go. Once again, I'm going to take this 1/3 times it by the 6. In this case, that gives me a 2. And then a 2 times an 80 is going to be 160. So we end up with the volume being 160 inches cubed. All right? Hopefully that makes sense. Again, very straightforward. It's just a matter of plugging numbers in once you've figured out the formula. All right, let's move on. What about the surface area? So surface area. Recall what surface area is. Surface area is, how much wrapping paper you would need to wrap this figure. So we don't care about, this, the amount of space inside the shape. We care about the surface area. How much wrapping paper you would need to cover the shape. Okay, so in finding surface area for a pyramid, and by the way, the surface area for a pyramid is slightly different than the surface area for a cone. Well, in general, I guess the general idea is the same, but the formulas are a little bit different. Okay, so what we're going to try to do is take the area of the base and we're going to add it to the lateral surface area. So remember, we're just taking the area of the base. That's pretty straightforward, trying to find the area on this. And then we need to find the area of the lateral surface area. Now, hopefully you kind of remember what lateral surface area means. It means kind of the distance around the shape, okay? Disregarding the base. We don't count the base, we just count the distance around the shape, or the area around the shape, you might say. So the lateral surface area is just representing, this triangle on this side. This surface area, what is the area of that triangle? But then also the area of this triangle back on this side, and the back triangle which would be back here, right? And then, of course, the front triangle. And I know this is getting messy, but this would be the front triangle. So the lateral surface area is just the area of all the sides, all the faces, other than the base. Okay? So let's find the area of the base. The area of the base is pretty straightforward, right? It's just the area of the base is a rectangle. So length times width, right? So 10 times 8 is going to be 80 inches squared. That is the area of the base. Now let's find the lateral surface area. Well, to find that, you know what? I'm going to back this up here a little bit. We're going to try to clean up this triangle because I made it pretty messy here. Because we're going to want to kind of be able to see a little bit more of this. So, real quick here, just rewriting this. The area of the base was equal to 10 times 8, which is 80 inches squared. Okay, so the lateral surface area. The lateral area, we'll just call it like that. The lateral surface area. Now, in order to find the lateral surface area, we need to find the area of one of these sides. And it's obviously a triangle. So think about what you need to find the area of a triangle. The area of a triangle is simply 1/2 times the base times the height, right? So if you're thinking of this triangle right here, right? This one right here, if I could just draw straight, we would need to know the length of the base. Okay, well, the base is going to be from here to here, and they give us that. That's 8 inches. Okay, that's the same as the side of the rectangle. So we know that the base is going to be equal to 8 inches. Now, the height is tricky because this height right here is not the height of the triangle. Okay, it's the height of the pyramid. Okay, and because the triangle is sitting slanted, it's not the same distance. Okay, so it's kind of like what we were talking about earlier with the cone. We're kind of looking for the slant height of this triangle. Okay. Well, actually, no. I'm sorry. I have to correct myself. We're not actually looking for the slant height either, because the slant height is going to be the length of this side, right? Which, well, yeah, yeah. So that's the length of the side. I'm sorry, I'm confusing myself here. So the slant side is going to be different than, let's say, the length of, or the height of the triangle. If I draw this dotted line, and again, maybe it'll help if I draw maybe a triangle that we're kind of used to seeing. So if I have a triangle that looks like this, right? Pretend like this triangle is the one that we're seeing on this pyramid. All right, to find the area for that, we need to know the base, which we've already said is 8. This side, from here to here, this is the slant height, you might say, okay? And even if we knew that, let's say it was 10, okay? Would that help us at all? Well, no, because that's not the height of the triangle. The height of the triangle is this, right? Straight up and down. This is the height that we're looking for in our formula, the height of the triangle. So the slant height is not actually going to help us either, okay? This height, this 6, that doesn't help us because that's something completely different. That's the height of the pyramid, certainly not the height of the triangle face, okay? So in order to solve this, they're going to have to give us more information. They're going to have to tell us what the height of this triangle is right here. So let's say they tell us that this height is 9 inches. Okay? Let's just say that. Let's say it's 9 inches. Okay? So, with that known, we now know the height of our triangle. And we can say that h is equal to 9. And we're ready to solve this. So, the area of the triangle would be 1/2 times the base, which is 8, times the height, which is 9. 1/2 times 8 is 4. 4 times 9 is 36. So the area of the triangle is 36 inches squared. Now, here's where it gets a little bit interesting. So if we have a right triangle, and that's pretty much what they're going to give us in this book, right triangle, again, meaning it's not oblique, it's not leaning one way or the other. If it is a right triangle, which this one is, then all of the faces are exactly the same. Okay? Well, I shouldn't say exactly the same. They're the same if the polygon sides are the same. Okay? So, in other words, this one here has 8, right? That's the polygon side. It's 8. Well, that would mean that this one over here on this side, this is also 8. Okay? So if these two sides are 8, well, then the triangles that these sides create are going to be equal because this is a right pyramid. If it wasn't a right pyramid, we could not say that. But because it is a right pyramid, we can say that because the base length here is 8 and this one is 8, then the two triangles, that they create on the face are going to be the same. All right? So this 36 that we have here, that would represent the area for this triangle, but it would also represent the area for this triangle on the opposite side. Okay? And you have to think 3 dimensions here, but on that opposite side. Okay? So there we go. Those are 2 faces done. Now this says a polygon as a base which has 4 sides in this case. So there's going to be 4 triangles. So we just solved 2 of them. Now we need to solve the other 2 triangle faces. So that would mean we have to look at this triangle face right here, right? This triangle face. All right. Now this triangle face has, and again, if we're looking for the area of it, the area of the triangle equals 1/2 times base times height. This base is 10. So we're going to have 1/2 times 10. Now what's the height? If this is a right pyramid, then once we know the height on one triangle, we know the height on all of them. All right? So once you know the height on one, you know the height on all of them. Okay? So this height is also 9. And if we multiply this out, we have 1/2 times 10, which is 5, times 9, which is 45. So we have 45 inches squared for this face. Now, again, because this back line for our back polygon here, the back line for that polygon, that's also going to be 10. Well, that means the triangle that it creates in the back of this shape is also going to be the same, going to have the same area. All right, so we have grand total here, putting it all together, we have the 80 for our base, okay, just one base, and then we have the 36 right here, which is the 2 kind of the side faces. So we have 2 of those, 36, and then we have the front and the back, which is this 45. So we have 2 45s for the front and the back. So we're going to add all that up. That is going to give us the surface area of the pyramid. All right? I know it's a lot of work to get there, but it's not that hard once you kind of understand the process. So if we add all this up, we end up with what? 22, 16, 24, I believe. So we end up with 242 inches squared because we're talking surface area. Okay? All right, so hopefully that makes sense. All right, now, we got that one done. Now let's look at the surface area of a cone. Okay, this was the surface area of a pyramid. What about a cone? Well, there's another formula here, but the good news is that it's not quite as complicated as the pyramid because it doesn't have as many faces. The pyramid has all of these different triangular faces. The cone, you might say, only has one face, and it's a curved face. All right? So this one really boils down to memorizing a formula. So the formula is the area of the base plus the lateral surface area again. So again, the general idea is the same as the pyramid. I mean, that part's the same. It's the area of the base plus the lateral surface area, area of the base plus the lateral surface area. The difference here is that lateral surface area is kind of complicated. It's kind of complicated to find the surface area of, or the lateral surface area of a cone. So we're going to just take it on faith right now. We won't go into the math behind it. You're just going to have to memorize the formula to find this lateral surface area. And the lateral surface area formula is pi times the radius times the slant height. And I guess we'll call that S for slant height. All right, that is the formula for the lateral surface area. All right, the lateral surface area. Okay, so pretty straightforward. All we have to do is plug numbers in. So now remember though, that this formula is only for the lateral surface area. And if we're trying to find the total surface area, we need to remember to add the area of the base. Okay. So what's the, I could say, I guess I should ask you, what's the whole formula for the surface area of a cone? Well, the formula then is going to be, and maybe we'll put surface area, is going to be equal to the area of the base, which, because it's circular, right, what's the area of a circle? It's going to be pi r squared. So that's our base, the area of the base, pi r squared. That's this one, right here, the area of the base. Okay, and we have to add that to the lateral surface area. So plus pi r s, which is this, the lateral surface area formula. All right, so to find the area, surface area of a cone, this is kind of the key formula right here. Okay, once we have that formula, all we have to do is plug things in. Okay, so surface area equals pi. Now, what's the radius of the base here? The radius of the base is this number right here, right? 5. So we have 5 squared, which is going to give us 25, plus another pi, r, which we already said was 5, and then s. And s they're going to have to give you. So let's say that s is a 6. All right? That's something that they will have to give you in the problem. And remember, this s is just the slant height. It's the length of this line. Okay, which I know I keep saying it, but it's important to remember that's not the same thing as this height. Okay, that's a different thing altogether. We're looking at the length of this side. Okay, so we have times r times that slant height, which is 6. And now we can just go ahead and multiply this out and then combine. So we have 25 pi, be the proper way to write that, write the coefficient first, plus 5 times 6 is 30, 30 pi. So 25 plus 30 pi is going to be 55 pi. And that is going to be the surface area. All right, so it's 55 pi meters squared. Boom. There it is. All right. So as long as you know the formula, the surface area of a cone is a little less complicated, I think, than the surface area of a pyramid. Because the pyramid, you're kind of adding up all these faces. And a cone, you don't have to do that because there's really only one face. All right? So make sure you've got all of these formulas written down in your notebook so that you can access them when you need to, when you have work on this in your seat work. Excellent. We will stop here today, and I will see you tomorrow.